I'll introduce the entrance tank just briefly today before we then go down the more specific path of how do you measure and control flow in a water treatment plant or indeed anywhere. So to get started, flow control and measurement, it's creativity without a trip, it's variations on a drip, it's giving head loss to slip, and it's chemical doses that don't dip. So that's what we'll be talking about. And entrance tank got added to this long list of things that we're going to talk about over the next 2 sessions. So entrance tank. So this entrance tank is what I was talking about, hot off the press. I just added the chemical dosing, the doser system to this morning. Let's look inside, and we're not going to worry about the chemical dosing system until much later, like almost at the end of the next session. Inside are all these pieces, and water enters through this pipe. And I should have made an animation here, but I got distracted. So water flows down into the entrance tank. I'm assuming you can follow my cursor. It's going to get deflected by this sloped bottom and end up heading over in this direction. And it's basically going to make a big eddy here and circle back and then go through. Here's some trash racks. Here's where the dose controller is for the chemical feed. It's picking off the water level there to figure out what it's doing. This long section of the entrance tank is about providing an opportunity for pretty high density particles, grit, like think small sand, for it to settle out so that it doesn't end up like clogging our flocculator. So things that would have settled out anyway in the plant, you want to catch them here so they don't settle out and give you a maintenance issue later on in the plant. And the way that the grit is handled is it's going to drop into these hoppers, and if the hopper begins to fill up, the plant operator can grab a hold of this 2-inch diameter PVC pipe, pull it up. That unplugs it from the socket that's embedded in the concrete in the bottom of this hopper. The socket is like a coupling that would normally be used to connect 2 pieces of pipe together, but that coupling socket is embedded in the concrete. So when the operator pulls this pipe out, there's a hole in the bottom of the tank that the solids can slide through and go down into this bottom part, which is this big channel that ends up dumping into the main drain channel for the plant. The next piece is the water exiting the place where the sedimentation is happening, goes to this linear flow orifice meter. This is a device that was specifically designed to get a linear relationship between flow rate and the depth of water in this tank, and we'll talk more about that later. So that's all happening inside this entrance tank. So for the entrance tank design, you're going to be thinking about, well, how big does the entrance tank have to be so that there's enough time for particles to be captured by them falling down? And to be fair, we're going to talk about sedimentation, I don't know, 4 weeks out or something, but it's not so complicated. You can just remember now that the trick for sedimentation is that the only thing that matters in a tank is the plan view area. So all that matters is the plan view area. That's what's going to determine how much sediment is able to be removed. And so it's looking down on this tank from above, what's the area that this plant provides for particles to settle out? It kind of makes sense, right? We're relying on gravity, and gravity's pulling things down to the bottom of the tank. And so it's that bottom surface area that matters. Here's the inside of where the trash rack is. And you might be thinking about, why do we need a trash rack? What's so important about that? Our trash rack is maybe even more important in our plant design than in conventional designs, because the very first place where water that goes through our flocculator and then is going into our sedimentation tanks, before there's really been any opportunity for more particle removal, the water is going into the sedimentation tank and it's having to flow through an exit that is about 3 millimeters wide. So there's a gap that the water has to flow through that's only 3 millimeters wide. And that means that our trash rack has to catch everything that's bigger than 3 millimeters. Otherwise, it's going to land in these diffusers that are in the bottom of our sedimentation tank. They're going to clog and it's going to be a maintenance issue. And here's actually an opportunity for some creativity. It turns out like this is one of these, like in one sense, it's a very simple device. It needs to provide a gap that's smaller than 3 millimeter and catch debris. Think leaves and twigs and fish and crayfish. It needs to catch all of that stuff before it would go further into the plant. And the various designs that have been built over the years have had problems. We weren't being detailed enough in our designs. We weren't providing a design that looked like this even. It was even less detailed than this. And so our partner in Honduras was trying various things to make a trash rack. And often the porosity, meaning the fraction of the open area, wasn't high enough in the systems that they made. And so the head loss was too high. And I'm wondering, given what we talked about lately, do you see the connection? If the trash rack doesn't have very much open area, then why does that make the head loss higher? And would you be able to tell me what the head loss through the trash rack, what it might scale with? And I think I'm going to ask you the question. Do you think the head loss through a trash rack is going to scale or be proportional to the velocity of water through the trash rack? Or is it going to scale with the velocity squared of the water through the trash rack? Ooh, think about that one just for like 15 seconds. Does head loss through the trash rack scale with velocity or with velocity squared? It does scale with v squared because it's a minor loss, or said even better, the loss is about the flow expansion that happens on the downstream side of the trash rack. So water contracts into these narrow spaces, it expands coming out the other side. And so that expansion is where the turbulence is generated and where the head loss happens. And that a head loss from an expansion goes with v squared. And by the way, I don't know if you picked up on this, but that's true even if the flow is laminar. It's like, oh my goodness, that's crazy. If you have a flow into, even if you have a pipe that's discharging water into a big lake, and even if the flow out of that pipe is laminar, all of the kinetic energy is lost when it flows into the lake, and that is v squared. So it always scales with v squared when you're doing an expansion. Okay, man, you guys make me happy. You got v squared as your friend now. So that the potential place for some creativity, and I haven't thought a whole lot about potential projects for this class, but we'll think about that as we get closer to that time. This might be a potential project. We need a good fabrication method for a trash rack that has a high porosity. And the way I'm showing a high porosity is, you can think of this as like guitar strings that are somehow kept tight. And that somehow kept tight is the part that I don't know how to do. So that could be a potential project to figure out how would you fabricate a simple system that allows you to have wires kept tight that would maintain that 3 millimeter gap. It would be easy to clean. Okay, I'm good with that. Here's another section view of the entrance tank showing what's happening inside. And I'm curious, do any of you have any questions? Like you got the idea, water is coming in out of this pipe. It ends up being chaotic at this front end. I'm not exactly sure what all is happening, but because of the way I've designed this, water's probably going around and then flowing back across in this direction, going through the trash rack, 1 or 2 trash racks, and then past all these hoppers where grit can be settling out, and then into the pipe where it gets into that pipe by going through little holes in the side of the pipe, and then goes down to the bottom of that pipe and exits and goes into the flocculator. And Michael's got a question.
I do, Monroe. First of all, very timely, because in your presentation last week, the students in Capstone, we saw this new entrance tank, which we had never seen before. But yeah. I'm curious if you could explain a little bit why. I understand the idea of the hopper, but was there anything to the geometry of the hopper, the height of it, the slope of it, that would be of interest to me?
That's excellent, excellent. Man, I would say, were you looking at my notes beforehand or what happened? So I'm not going to answer your question. I'm going to just keep right on going. This is about design thinking. And Michael asked a perfect question, like, well, where did that height come from? And that's actually a really good question, because if I tell him I looked it up in a book, that's not very helpful to Michael. It doesn't really help explain, like, well, where did that come from? And if I say, oh, it doesn't matter, then Michael knows that I don't understand physics, because it always matters. And that's like a key insight. When you're designing something, there are no random dimensions. There aren't any dimensions that it's just like, oh, you can pick anything you want here. There's always something that constrains it. So no dimensions are arbitrary. There are always constraints. And this is true whether it's an evolutionary trait like the diameter of your femur, or an engineered device like the diameter of a bicycle wheel. In all cases, there's something, and you shouldn't have to think too hard to figure out like what might be constraining each of those. So what's constraining it? Often it's physics, or for that matter, biology or chemistry. I had a physics minor, and so I tend to think of the world as it's all about physics. I know that the microbiologists would disagree with me, but anyway, so I say it's about physics. And there's Michael's question, like, well, what about that slope in the hopper? Where did that come from? Well, what would you like? What would you like to have happen in this hopper? You would like it if, when you pull the plug out of that hopper, you would like it if the hopper would drain, meaning all the sediment that's sitting there would slide down and go out the hole. And this is very similar to, I don't know if you have, are there any places in Ohio where there are cliffs or where there is hillsides where there is, I think it's called scree, where there's like rubble coming off the side of a mountain, and the slope that you get it's the angle of repose. It's the slope that you get that's just barely stable. And usually where there's scree, and if it's close to a hiking spot, there'll be signs there. Don't hike on this, because the whole thing is just waiting for an avalanche, right? You don't hike on scree. Well, we're trying to create a system where all there is it's avalanche ready. It's steep enough so things will slide down. So if I look at that, it looks like my angle is probably 50 degrees. which is also what we use in our sedimentation tank. It's steep enough that just about anything will slide down that steep of a slope. And then you might say, well, how did you decide how many hoppers to have? Or like why didn't I make those hoppers even taller? And if you think about why not make them taller, which I could easily do, like I had the space, in order to make those hoppers taller, I would just drop this, I would move the bottom of the system down further. So anybody have an idea? Why wouldn't I make the hoppers a whole lot taller? And so I could have done this with one hopper. I could have just had one big hopper. Why not? It would work. Okay, I think the last time we met, I suggested this idea of be an extremist. And it's like take things to the extreme in both directions and see what happens. So here I'm saying go to 1, which is as far as we can go. We can't really go to 0. That doesn't make much sense. We go to 1, and you could also go to infinity on the other end. And can you tell me what happens to the volume of concrete required to build the hoppers as you vary from an infinite number of hoppers down to 1 hopper? This is kind of a fun result. Can you see it? Can you draw the picture in your head? What happens if you have infinite number of hoppers? How much concrete do you use just for the hoppers? Wait, what does it look like? The hoppers are a nanometer tall, and they're along the, maybe I didn't actually hear what you said. In any case, the answer is not much. It goes to 0. The concrete that's in the mountain goes to 0 if you turn that mountain into an infinite number of mountains that are a nanometer tall. So I'm not sure if you believe me. Do you believe me? Are your thumbs up, or are you like, how about it in this case? If I have my 1 nanometer tall mountains, the area under the curve is at most, well, it's half a nanometer. I've got a half a nanometer average height of concrete. Okay, so it goes to 0. So infinite would be the way. Economics would tell you that if you're just trying to save concrete, you should go to an infinite number of hoppers. And economics also tells you that going to just 1 hopper is the worst solution, because that's when you have the most concrete. So that's one reason not to just use 1 hopper, is you have to put a lot more rubble and concrete in place to make that. Going to a small number of hoppers also means that you have to buy more pipes, because you need a little plug for every hopper. And of course, we come up with some unrealistic situations here, but you end up having too many pipes if you have too many hoppers. And then the other thing is, you would like if a plant operator can grab a hold of the top of this pipe, pull it out, let the thing flush, and then put the pipe back in again. That means that the pipe should be like human length. It shouldn't be really, really long, or it's going to be hard to like get it back into the hole again. So that's another constraint. And by the way, you might think here, okay, we're being super spendthrifts in that we're not putting valves on this. This is one case in the plant where, yeah, you could put valves on this, but it would be a disaster. Because what's being removed here? All this gritty stuff, including small pieces of gravel that get brought in from your water source. And if you had a valve in the bottom of these tanks that you would open up and then close down again, eventually you would get some piece of gravel caught in that valve, and you wouldn't be able to get it closed, and the operator would get frustrated and it would crank even harder, and you'd have that valve broken. So the cheap solution is actually the easiest one to maintain. Wow, I think I might have answered Michael's question. It is a case where like, should it have been, I guess I have 1, 2, 3, 4 hoppers there. Should it have been 3? Should it have been 5? Where you'd have to like really go into optimization of cost to figure out that one, which is kind of cool because now we could actually do that. Now with our system, we could make the change and see how much the cost changes to see which end up being the cheapest option. Of course, we're not taking into account labor when we do that, but we can at least get a sense. So that's one thing. Another constraint besides physics is economics, which I just mentioned about, like, you don't want to use more concrete than necessary. Another one is fabrication. Oh, economics. I think I pulled up the diameter of that overflow pipe, and the diameter of that overflow pipe is partly determined by economics as well, because a bigger one would work even better. So there's two constraints that fight. There's a hydraulic constraint that says it has to be a certain diameter in order to carry the water that might come into this entrance tank, meaning the plant flow rate, and dump it. If the two trash racks, or if the trash rack completely clogs, that's your worst case scenario, and that overflow better be able to dump all the water coming into the plant so that it's not just spilling out over the floor. So there's a hydraulic constraint, and then the hydraulic constraint says that anything bigger than, I'm guessing that's a 4-inch diameter pipe, anything bigger than 4 inches is great. And then your economics constraint comes in and says, okay, but I'm not going to put a 20-inch pipe there because that costs me a lot more money. So economics or resource efficiency is always there. And then for an example of fabrication, if you look at the top view at the top of the slide, it has to be human scaled. So this tank has to be wide enough so that a human can get in it to fabricate it. And that ends up being a really entertaining constraint, because if you have a channel that's only 15 centimeters deep, then a human doesn't have to get in it to fabricate it. And so a channel that's only 15 centimeters deep can be fabricated even if it's only like a little bit more than a hand wide. So a shallow channel can be fabricated when it's hand wide, but once you have to actually get your whole body in there, then it's the dimension of your hips and maybe a little bit about how much your elbows have to move around while you're fabricating that ends up setting how wide is reasonable before the masons that have to fabricate this start complaining about how this is impossible to build. And believe me, like those are issues that you absolutely have to think about when you're designing things. If you design something that can't be fabricated, you're going to be famous on the job site, and you don't you don't want to be famous on the job site in that way.